So what we are going to do is, now we started talking about this successive loop closure, and let me reiterate, at the end of the day, any flying robot, the process for controlling any flying robot is the same. As a matter of fact, out of those 12 equations that we talked about, those are the 12 equations, fundamental equations for a flying body, no matter what the shape of the body is. Out of those, 6 kinematic equations, which are independent of mass, external forces, and movements, are going to remain the same. Last 6 equations, basically the dynamical equations of motion, are going to remain the same. The only thing that would change in those 6 equations is 3 forces, Fx, Fy, Fz, and 3 moments, Mx, My, and Mv. So you can take whatever you have studied, you can take those equations just like that and perform the complete analysis on a quadcopter, as a matter of fact, on an octocopter, as a matter of fact, on maybe a spin wing aircraft, or maybe a tilt rotor aircraft that can transition from helicopter to plane. And at the end of the day, the process for designing the autopilot for simple flying bodies, which means they are not extraordinarily maneuvering or they are not doing complicated maneuvers, is also the same. So, and I will show it to you towards the end of this class, that the concept that we have studied, that how do they translate to any different aircraft. Once again, please download the BH quadcopter. Basically set the variables, but do not play with that knob. Let that knob be where it is. Okay. So don't start, because that thing is super addicting. Once you start looking at it, you will just continue doing it. So, okay. So that is part of a slightly different active learning module that MATLAB has given us. So I would like to show it to you how to use, and then I would show you what we can do with it. Okay, so we are on, this is what we are talking about. We talked about, we have the lateral control. In the lateral control, we have the innermost transfer function. Then we have a transfer function that is next to it. And we have the transfer function that is the outermost transfer function. And at the end of the day, what we want to do is, we want to control the course angle. And the difference between the course angle and the heading, and that will happen for any flight vehicle, is presence of wind term. If you have a flight vehicle that has wind, then basically, even though your flight vehicle heading may be in 10 degrees, but the wind may push it to 5 degrees or 15 degrees. And that 5 degrees or 15 degrees would be the course. That's why whenever you talk about in aircraft, you say, pilot says we have to do a course correction. Course correction means correcting the course, not the heading, correcting the course. Okay, so first and foremost, what I want to do is, this is the overall transfer function. And in last class, I kind of drew this. I didn't draw the complete transfer function. So what I want to do first is, I want to draw the complete transfer function starting from the beginning. So first, we have the set course, which is controlled course. Then we have a summing junction. Then we have a proportional gain, Kp, which is on the course. This guy gets fed over here. We also add an integrator gain onto the course. So basically, you have Ki, which is Ki course divided by S. This whole thing gets fed into this summing junction. And please understand, since these are the controller terms, both these controller terms are positive. Then what we have is, and let me go here and tell you what is happening. We have course here. At this point, we are getting an error in the course. error in the course gets multiplied through KP and integrated term. It's get added over here. And what would happen is after this, you are gonna have something called as the uh, the role. So basically, this is what is going to happen. So this is the C, which is the control role that gets fed to the next summing junction. At this summing junction, you are gonna have actual role coming in. Actual role that is coming in. Try again. So, and that is going to get fed into the aileron output. Then this aileron out sigma C, so yeah, the error phi. This error phi gets fed. It's a long transfer function. Proportional gain on phi. Another integrator gain on phi. So which is Ki phi divided by S. These two terms get combined over here. So this is plus, this is plus. Then what happens is you get an aileron feedback. Then you have another summing junction that gives you the actual aileron input. Then you have this transfer function, which is A phi 2 divided by S plus A phi 1. And once we do this, what happens is we get P. Then from this P, we integrate and we get 1. So 1 over S, that gives me phi. And then I multiply that by the term G divided by VG and integration of that. And I get the actual course. And now comes the time to close the loops. And this loop closing is going to be a little complicated, but bear with me for a second. We are going to have a KD phi term here. We are going to have unity gain feedback over here. And then last but not least is we are going to have the actual heading on the negative side of the set heading. So now let me explain this loop. And this loop looks intimidating, but it's actually not. This is something that came from all the equations that we derived so far. The only difference here is we have added the controller. So we have, first and foremost, we have the outermost loop. Outermost loop is comparing the actual course. This is the actual course to the course that is set. So this is what you are getting here is the actual course. And what you have here is the set course. And here, what we have, we get the error term. This error term, this is the error term. E is nothing but the actual course minus the set course. So this error term gets multiplied with kpx. And then this is proportional control that gets fed onto the summing junction. One thing I want you to understand is this actual course gets fed to this integrator term, and you have an integral control that is not acting on the error, but the value itself, the value itself. And some of you may ask me why? Because if the course is, so basically what's going to happen is, if the commanded course is higher, then what's going to happen is the integrated term is going to control it. If the difference between the commanded course and the actual course is small, then what's going to happen is the KP term is going to control it. So if you want to minimize the difference between the commanded course and the actual course, the KP term would play the role. But if you want to look at how far the commanded course is deviating, or how fast the commanded course is going away, so that basically the integrated term will take care of. And once you actually feed all that, what happens is you have this phi c, and this phi c is the commanded role input. This is the commanded role. This is commanded role. And this commanded role gets fed into the summing junction. And this summing junction basically feeds the role that is coming from this outer loop. Then here we get something called as the error in the role, which is the difference between the commanded role and this is the actual role. This error gets fed to KP. Same logic. This error, as you can see here, this is plus and this is minus. This is plus and this is minus. This error gets fed into this region, and then what happens is you feed it forward, and then what you have is you have the actuator input. Then the next part to it is basically here you're going to have negative signs, and this delta A gets fed to the transfer function that multiplies. Actually, once you add the transfer function, you get this. Actually, I drew this incorrectly a little bit. So like this, and this is like this. So actually integrated term is also acting on the error. So my apologies. I didn't draw this correctly. Integrated term is also acting on the error. Here also the integrated term is acting on the error. Yeah, this is correct. And then what you have is you have this KD term, which is the derivative gain. Then you integrate that, you get the value of phi. Then you multiply with G divided by VG times divided by 1 by S. You integrate and you get the actual course. So this is nothing but actual course. Now, if I want to control this, the steps are combined everything. So go from the beginning all the way to the end and control or design the loops so that you can tune the gains that are present. So what are the gains? You have KD and you have KP role. So KD phi and KP phi. You have KI phi, and then you have KP chi and KI chi. So you have some gains on the course. So these are the gains on the course. These are the gains on the role. And this is the integrator on role. So the way you would do it is, and I would discuss this step by step. First and foremost, you want to go with the innermost loop and close this. So we are going to close this loop. Then this would be the first step. So this is, you would do first. Then you will do this as second. Then you will do this as third. Then you would actually find out this fourth. and you will do this fifth. So if you want to tune the gains for the lateral dynamics to control course, what you will have to do is you will have to go all the way from K phi and then all the way to KPX. So that is how these loops will be closed. Now, what we do is in the last class, we talked about the generic process on closing the loops. So first, I'm going to close the innermost loop. The innermost loop is this guy. So basically, the innermost loop is theta. So I will write this over here. Phi divided by phi c. And this is also called as the transfer function h phi divided by phi c s. And if you reduce the block diagram algebra, if you perform the block diagram algebra, you will notice that this guy so what you can do is if you reduce this, this comes to Kp phi a phi 2 divided by s square plus a phi 1 plus a phi 2 Kd phi s plus Kp phi a phi 2. Now, believe it or not, this transfer function is of the same form that we have been talking. So this transfer function is of the same form that we have been talking, which is omega n square divided by s square plus 2 zeta omega n s plus omega n square. And omega n square is this guy. And if you look at this guy is 2 zeta omega n. So what you can do is you can tune these values Kp, basically just tune the Kp theta, Kp phi and Kd phi in such a way that you have control over the gain of the transfer function and the poles of the transfer function. So basically, you have an outlet next to you, you know, right? Okay.
I do now.
Okay, good. So, okay. So basically you can control the gains or the performance. And ideally what needs to happen is something like this. And I want you to understand, at the end of the day, no matter what happens, we want the output is equal to input, which means if I set my input, in this case, if I set my Cc as 0 degrees, then somehow my output, finally, the steady state output should be 0 degrees. What that means is if you were to look at the step response of the system, then what should happen is these gains will control the amount of time it takes to go from 0 to the steady state, and the damping would also control the amount of back and forth that system will go around the steady state. So what is going to happen, and let me pick up my model, is if you want to control, then what's going to happen is you have course, and please understand, some of you may ask me, we are talking about the course, and then why this role is coming in the picture. The important part here is, if you look at the aircraft dynamics, you cannot purely set the course like this. If you set a course, once you set the course, because of the yaw and roll coupling, you have a course that will give rise to some roll. So what we need to do is, in order to set the course, And then what will happen is, in turn, that role is connected to your yaw. So basically your course would change. And if you have your simulation working correctly, you will observe this. Basically, what will happen is, this is what you will notice. If you have a simulation, if the aircraft is in level flight, everything is fine, it will work fine for some time. But then if you have wind terms coming in, what would happen is, because of the wind, first aircraft would change the course. And then what would happen is, aircraft will roll. And then because of this rolling, again it would change the course. And then it would roll. And finally, it would crash. You should be observing some dynamics, something similar to this in your simulation. The only way to check if your aircraft, if your simulation is working well or not, is set the wind is equal to 0. So this is a test case that you can run. Set wind is equal to 0, which means no wind input. Set a constant value of thrust, not a very high value, just a sort of 0.5 value of the thrust. And basically add a very small value of angle of attack or pitch. Add a small value of pitch. And what you should see is, your aircraft should be able to hold the level flight for a long time. It may basically it may go up, but at the end, let me see. Since okay, it's an Aerosonde parameter. So basically, what you would notice, that aircraft should be able to maintain the level flight for some time. And Aerosonde frame, if you look at it, its CG is located up front. Its CG is located up front. So by design, it's stable. So what you're seeing, that your aircraft going and then becoming unstable, is most likely because of the wind values that you're putting, or the values of the side slip angle beta that you have put in. So change, make side slip is equal to 0, which means basically aircraft is not going like this. Make the wind values, input to the wind value should be 0, and provide a small non-zero value of thrust, and see if your aircraft can maintain a level flight for a long time. Your aileron should be small values. Your rudder should be at 0. So try that and see if it works. That is one way to check it. But unfortunately, in real life, that doesn't happen. As soon as you add the wind, what's going to happen is that wind is going to change your course, which means when you add the wind, your heading is no longer course. So your course is something else. Because of that course, aircraft is going to roll. And then that is why that roll dynamics comes in the picture. Everyone understood this? Okay. That's why I wanted to spend time on these equations. And what I want to do is, at the end of the day, this is, so I'm looking at the roll. So what I'm looking at is, this is the commanded roll, and this is actual roll. So what I'm going to do is, I am going to set up the values of KD and KP. I'm going to set up the values of KD and KP in such a way that this roll disturbance, so basically I get 1 at the end. Everyone understood this? Once I get at the end, I'm not looking at the transient state. When I look at the steady state, I need to get 1. And that is the true meaning of loop closure. Everyone understood this? Remember this. You will need that for even quadcopter design. Okay. And then next question is, how do you decide what is the practical value? If you plug in this equation inside MATLAB, MATLAB has a fantastic gain tuner. MATLAB will give you certain values. But how do you know if those values can be implemented on the airframe? Because remember, your airframe actuators, they saturate. So what happens is, in that case, you find out the value of Kp. So look at the disturbance. So the maximum disturbance or maximum error is going to be at the beginning. Do you agree with me? So this guy is nothing but Emax. This guy is nothing but Emax. So I find out the value of K phi as nothing but delta A max, which is the maximum actuator deflection that I can achieve, divided by E max. And please understand, you can have, since your actuators can go up and can go down, since your actuators can go up and down, what you need to do is you need to add the sign, which is whether it's plus or minus, SIGN. So SIGN, my own reference, -1 is minus, or SIGN -5 is -1. SIGN +5 is +1. Sine of A P theta 2. Everyone, yeah.
Function or is this literally just the sign of the number?
Sign of the number. So basically minus, so, and this function is implemented in all libraries. So just if you see SIGN function, SIGN of -5 will give you -1.
Why is it?
Just sign off that function.
Oh,
Minus.
okay. Oh, it just tells you. Oh.
Okay. Okay. And then sometimes what you want to do is you want to control something called as the roll loop frequency, which means the aircraft changes the course, starts rolling down. But now what you have is you have these controller gains. So aircraft is going to do something like this before it actually stabilizes in the roll. So what you can do is by adjusting the values of damping coefficient and Kp, you can find out the value of, you can actually tune it. So so here is something that I want you to understand. If you have just a UAV, which is not carrying passengers, you really don't worry about what type of oscillation it has. But then if you have a passenger aircraft, or if you are carrying passenger, this roll frequency is not desired. You want it to be as stable as possible. But also you don't want it to be responding to it very quickly, because then human bodies will feel uncomfortable and basically will get motion sickness. So what you want to do is you want to design the value of Kp in such a way that the natural frequency, so the aircraft kind of turns, or basically you get a course, sort of you have the roll instability, and then gradually it kind of slowly it goes back to its required heading. Everyone understood this? Okay. Now the next part is we now want to go a step further. See, if we have disturbance that we conveniently ignored, if we have disturbance on the roll, what's going to happen is the roll will be having some type of changes or perturbation. Now, what is this disturbance on the roll? Remember, the dynamics of the aircraft is actually nonlinear. And the way we try to approximate it, we linearized all the terms, try to make a transfer function, and everything that was left, we treated that as a disturbance. But those terms are present. Those terms did not vanish. What that means is, even though this approach is fantastic, when the linearization is perfect, in practical cases, we are going to have some nonlinear effects coming in. And these nonlinear effects would actually destabilize. So if you look at the actual transfer function, so for an example, if you add some type of a disturbance, what's going to happen is, this may be a little bit, so you will add the disturbance on the roll. This is coming from here. And this we studied in chapter 4. So you get A divided by A phi 2. So you get this. This is where this is coming from, the nonlinear terms. And now what that means in actual practice, that's why you have something called as, I didn't mention this earlier. What you have something here is you have delta A prime and you have delta A. So I want you to think about what you have is you have external disturbance, which is because of the nonlinear effect coming on, and delta, the difference between delta A and delta, the difference between delta A and delta is actually cancelling the external nonlinear disturbance. And then what delta A that is getting fed is actually controlling the dynamics of the UAV. Everyone understood this? So we are adding a little bit of more control effort to compensate for the variation in the dynamical system. And that happens all the time, because if you think about it, the aircraft, initially the aircraft is heavy. As aircraft flies, the fuel is burnt, which means the aircraft mass drops down. In other words, the original dynamical equation is no longer valid, which means there is some error that is coming in because of the variation in the model itself. That error is also treated in that dP2 term. So unmodeled dynamics and again the nonlinear effects are actually included in dP2. Everyone understood this? You would see little bit, no? Yes? I'm spending a lot of time on this because I tell you, this is what I exactly did when I designed the flight control system for Bell 609. And at that time, I did not realize that how critical it is to get this fundamental understanding. But these fundamental concepts are super duper important. And then you can apply to Bell 609 program. So yeah, Bell Helicopter is a great place to work in Texas. It's in Texas. It's very cold, so I won't go over. Anyway, and then last but not least, since you have a second order transfer function, now let me write the transfer function with disturbance. So same thing. Now the transfer function is going to change because in this transfer function, I did not include the disturbance. But in the next transfer function, I'm going to include the disturbance. So the transfer function is going to change. And this transfer function will have two components. Actually, this is important. So I need to write this now. So now what has happened? We are considering unmodeled dynamics, which is variation in the fuel mass and nonlinear effects. In dP2. So once you do that, the same transfer function phi by phi c will now needs to be written something like this. You cannot combine dP2 and the other term together, because please understand, dP2, what we did, we have this nonlinear function and we just gave a linear variable to represent that whole nonlinear function. You cannot take that and put it along with all the linear terms, dollars to dollars, pesos to pesos. So what we do is we write transfer function something like this. P1 plus A, P2, KD, S plus A phi, KP phi. And here you multiply that by dP2. This is the nonlinear effect or the disturbance. This is the disturbance. Because please understand, now this transfer function has this dP2, and what we do is we take this out from here and we represent this separately, something like A phi to K D phi divided by S square plus A phi 1 plus A phi 2 KD phi S plus A phi 2 KP phi multiplied by phi C. So please understand, phi C is the input and you have the disturbance. So the total transfer function will have a component that is related to the disturbance input and the other component that is related to the control input. Okay. Now what needs to happen is, at this point, you have to see what type of disturbance is it. Is it a constant disturbance? Is it a ramp disturbance? Is it a white noise? What type of disturbance is this? And then adjust these gains so that you are able to compensate or cancel out that disturbance completely. So basically, somehow you tune that so that that disturbance goes away. Typically, once you have Kp and Kds gained or gains tuned, then finally that disturbance will give rise to something called as the steady state error. That's steady. So that is the primary purpose of the control system designer, that even though you have a disturbance that is varying, at the end, either that complete disturbance should go away or it should get converted into a constant steady state error that we can quantify and cancel out. Steady state error cancellation is easy. You add a simple integrator term that you turn on, not all the time. You add a simple integrator term that you turn on when you are reaching the equilibrium position. If you turn it on very soon, then what will happen is your error will continue to get integrated. What it means is the controller effort from the integrator would continuously increase, and that would lead to something called as integral wind up. Wind up means completing the full circle, going back. So that is the meaning of wind up. So once again, if you turn on your Ki integrator term when the error is huge, what's going to happen is that huge error will continue to get integrated with respect to time. That means that is going to give you a huge quantity. Even your Ki term is small. Since you are integrating with this huge quantity, it's going to give you a huge control input. What that means is, even though you get some control input, because of the actuator saturation and other stuff, that control input cannot be implemented in the actual control system. That is nothing but integral wind up. Everyone understood this? Remember this. But if you have a small steady state error, then what you can do is you just initially you don't turn the integrator on. As soon as the steady state error reaches beyond certain threshold, you turn the integrator on. Integrator will take off the steady state error. As soon as error all of a sudden increases, turn off the integrator, let P and D terms do their job. And when you have the steady state error, small steady state error, turn the integrator on. Integrator will take care of the steady state error. Everyone understood this? Yeah. Yeah. Yeah, delta A times T multiplied by Ki is the controller input. Right. So basically you have, because time is increasing, your integrator, the error will keep on increasing. Well, it depends upon the type of disturbance, whether it's a short duration disturbance or if it is a continuous disturbance. It completely depends upon the type of disturbance. Sometimes you can have a ramp disturbance. You can just have a step disturbance. For example, loss of fuel. Fuel is gradually reduced. So basically that error, the modeling dynamics is gradual. So any questions here? This stuff is super important. Okay. Okay. I know this stuff is important, but boring. So what I want to do is, I want to make things a little bit interesting. And I'm going to show you what we have all been waiting for. But before I start, let me ask you, did anyone turn the knob? No? Very good. Oh, very good. Very good. So what I want you to do is, I want you to go to demo files. then start BH startup, then run. You have to change your folder. And it's a huge, it's about, and then here comes the knob. Now, what I want to show you is, this is the template. This is the template for designing the control for any flight vehicle. If you want to do it, you start with the inertial properties. Then you decide, you look at the rotational matrices. Then you look at the Euler, depending upon what type of formulation you want to use. If the aircraft is not going to do 90-degree pitch, then you are well okay, you are fine with Euler. If you don't want, if your aircraft is going to perform super complex maneuvers, or if it's gonna go to 90 degrees pitch or come back or flip, so the flip means basically aircraft goes to 90-degree pitch. That is also a dangerous condition, because please understand, we are working in the discrete time. So even though the aircraft is at 90 degrees for a very short period of time, that will give an error in the actual computation, and it will give you some type of exception in the processing. So if you expect your aircraft to do complex maneuvers, go either to DCM, which is direction cosine matrix derivative, or you can go to Coutonian. So these two formulations you can use. Typically, Coutonian formulation is preferred. Then what you do is you derive the ordinary differential equations. Let me tell you, these are the exact same 12 equations that we studied for the fixed wing. Then what you do is you calculate F and TQ. These are the forces and the moments. For quadcopter, only value of forces and moments will be different than the fixed wing. Then what you do is, if you have an electrical plant, if you want to do the electrical modeling, just to understand what is the battery, what is the size, everything, you actually can perform the electrical motor analysis. Then what you do is you linearize the model and you control it. Everyone understood this? Then what you do is basically implement that on the full model. And if you want to go a step further, what you can do is you can actually generate a code that you can flash in your microcontroller that will implement the autopilot. You can do everything with respect to the Mambo platform that we have. We can do that even with the fixed wing. The only problem is we can't fly fixed wing here. And even though your controller may be working, your simulation may be working, unless you fly it over a large duration or a long distance, you will not really be able to see the control surfaces, action of the control surfaces on a fixed wing. So that's why we are using this quadcopter, and we will perform this on the quadcopter. And then I want you to go and fly the quadcopters in the drone studio, not just fly it, basically track it. So you will be trained on how to use the optical motion capture system. That is a very important skill that you should learn. Basically how to add the markers, how to create the model, and then how to get the data, and then you can compare the position that is reported by IMU and optical flow, and then compare the position that is reported from the optical system and see how well, how good, how bad they are. Everyone understood this? Okay. Online students, any questions before I start this? And when I teach you, I'm not going to teach you the quadcopter dynamics as yet, because I need to finish the fixed wing design completely. But quadcopter will follow exactly the same process. So first and foremost, I want you to check your system. And then check your installation. So basically, it's going to go through and make sure that you have all the toolboxes that you need to run this project. If you do not have the toolboxes, please install them before running. Otherwise, your simulation won't work. Question?
Just look at the installer. And it's giving a red marker for MATLAB, so. Is it just due to?
R22B.
Uh,
Okay. Why is it giving you red mark? I don't know. Just we will see. So basically, turn the knob, and once you turn the knob, patiently wait, and this live script will come up. Remember the long discussion that I had in robotics 1 about the principal components of inertia, and a short discussion I had in robotics 2 about the principal component of inertia. This gives you a visual representation of what principal components of inertias are using potato. So look here. So you have two potatoes, and the axes are different. One is principal, one is non-principal. The key takeaway here is I want you to read through this carefully. It's a lot of fun. Read through this carefully. It summarizes all the discussion that I had in robotics 1 and robotics 2. But at the end, the thing is, it relates that principal component, basically the inertia problem with the eigenvalue problem. So I would encourage you to take a look at it. And we talked about this, but this will be a nice refresher on what that is. So read through this. And then most important thing is, whenever we are designing an aircraft controller, we want to work in the principal moments of inertia, which means what we want to do is we want to find out the inertia matrix when we are at the center of gravity of the aircraft. That will minimize the cross terms, and it will make our life easy. So you can see when you are looking at the principal moment of inertias, all the cross terms would cancel and you will only have the diagonal terms. Otherwise, your dynamical equations of motion will haunt you. It would be complex. Sometimes it is not possible to derive the equations of motion at the centroid. And the typical case is if the mass of the vehicle is changing in flight. And in that case, you have no other choice than to start with the initial center of gravity and then propagate the changes in the center of gravity throughout your inertia matrix. And that gives rise to some interesting time varying equations that I did my PhD on. So if you, and then what I want you to look at is, remember we talked about the vector, rotation matrices, and then angular momentum in different frames. So this gives you a very nice explanation. What happens to the angular momentum when you look at the principal frame or the principal axis and non-principal axis. So they call it something called as the body frame B and the principal frame P. So this material we discussed, but I would encourage you to take a look at it and then see what is all that. And then it will show you the unit vectors in B frame. It will show you the blob, inertia tensor, and then so actually, who knew a story about this is not new, you knew. Who knew a story about potatoes could be a lot more fun. So read through that. And there are these questions. I would strongly recommend, even though it is not required, my recommendation is try to answer these knowledge questions, because this material you have to grok. You know what grok means? Master to the core, so you won't forget it. So if you don't remember anything from robotics 2, but you know, if you understand this pipeline, that's all I ask. You can do any vehicle, no problem. Okay, since we rotated the knob, now the next part is Euler equations or Euler parameters. These are not parameters, Euler angles. So passive rotations and Euler angles. Again, I spent tons of time in robotics 1 and time in robotics 2 just talking about the passive rotations infinitesimal rotations which are commutative, large rotations that are not commutative. But I want you to go through all these. And then, yeah, if you want to see the actual movie, there is a nice movie that will be played showing that why the large rotations are not commutative. If you change it to small rotations, you will see that the rotations are commutative. And then you can actually go through that. Remember, this is what we did in robotics 1 when we started rotation transformation. And then these are derived. Then these are the 3 successive orientation. Remember chapter 2, we talked about this, yaw, pitch, and roll. So you have RZ1, RZ2, and R3X. So Euler angles, these are the classic Euler angle triad that we use, which is ZYX. In robotics, we use this triad, this sequence ZYX. And then understand, you have the rotation phi, then you have the rotation theta, and you have the rotation phi. So you have, psi, theta, and phi. And when you multiply all these, you get your direction cosine matrix. Remember, these are Z, Y, and then what you get is this rotation matrix, the rotation transformation is exactly the same rotation transformation that you have seen for the spherical wrist. And this is exactly the same rotation transformation that we studied in chapter 2. Then you go down, and then what you do is you have this direction cosine, and then this is the relationship between the body rates and Euler rates. Please understand, Euler rates are inertial rates. They are defined with respect to the fixed inertial frame, and body rates are the rates in the body coordinate. We can't measure inertial rates. The IMU and the gyro on the flight vehicle will measure the quantities in the body frame. So if you go down, it will also do this. And then finally, it will come up with the kinematic equation. So at the end of this, what you're going to get is you're going to get a kinematic equation. If you use the Euler angles, you are going to get the singularity at 90 degrees. This is actually explained very well. But the last part, what I want you to play with is basically you can create a symbolic equation. For example, if you want to say, in one of these assignments in Mambo, I asked you to develop a controller that is a little bit exotic, okay, or a nonlinear controller. Rather than implementing that onto the firmware, what you can do is you can ask MATLAB to create the Simulink block. You add that Simulink block to your actual code, and then use MATLAB coder to create the C file, and then you can burn it on a flight platform. You can do the exact same thing with PicHawk. MATLAB has a direct pipeline to the PicHawk. You can connect PicHawk to MATLAB and actually have the whole thing do, you can implement the model. So you can create a reusable function, and then basically you can create a reusable Simulink block. And next part is, how is this getting implemented in the quadcopter model? I will talk about it when we study the quadcopter, but please understand what this is talking about is this is nothing but implementation of the kinematic equations for the flight vehicle. Now, if you want to develop these equations in direction cosine matrix, so if you assume that your aircraft is going to go to 90-degree pitch or very super complex maneuvers, you can actually do the direction cosine formulation, which is you have that big matrix, 3x3 matrix that you propagate. And I would strongly encourage you to read through all these. And again, it gives you an example of the potatoes. So read through all that, and then you will see how you can propagate a direction cosine matrix. So if you want to implement your code not in quaternions but in direction cosines, you can do that. And then finally, they talk about the implementation, and this is how the DCM implementation is done. So, and I want to tell you that this block is available in aerospace block set. So if you decide to work with the aerospace block set, you will have this block available. But this is what we talked about. The next part is if you want to implement in a Cottonian, again, it doesn't give you theory, but specifically what it does, it gives you the Cottonian block, wherein you can use the Cottonian block, change the vehicle parameters, you can change and then just feed 3 forces and 3 moments, and now you got all the parameter or the output that you can feed to your simulation. So I would encourage you to play with this. And then next part, believe it or not, those are the same equations, 6 equations that we talked about. I want you to look at the first equation. This is the application of Newton's law. Force is equal to mass times acceleration. And second equation, remember the inertia tensor multiplied by the rate of change of angular velocity, which is angular acceleration, plus omega cross I times omega. I derived this. Same equation, no matter what happens, what flight vehicle it is, you will have these equations. 3 equations for forces, 3 equations for moments. And then what you do is you go down and it basically talks about how those equations get derived. And we spent a lot of time deriving these equations, talking about it. And at the end, what you have is you have these equations. And then you will see you can use them in Simulink. And then finally, you look at the how to implement that in the quadcopter. Next part, that is where the things become a little bit different, is how do you calculate forces and torques. Please understand the forces, 3 forces and 3 torques on the quadcopter, they are different than the fixed wing. So you will see that this is particularly implemented for the quadcopters. But if you want, you can go in this function, take your forces and moment function, put it in here, and everything would work. So I would actually just go through that. Again, to find the thrust, you do the regression fit, and then you do all this, you get the torque. So this is pertaining to quadcopter, but basically this is how it is. Because quadcopter actually only has 4 motors. So it only has the thrust and the torque that are generated from the motors. It does not have any other control surfaces. But if you want to develop an exotic quadcopter, which I think Rice Lab is developing, you can add the flaps, and then basically those flaps would act as the control surfaces. So in addition to the quadcopter motors, you would have the control surfaces that would make that quadcopter fly forward, backward, leftward, sideward, something like that. So it's the last, yeah. Then next one is electrical modeling. Then you have linearize and control, and then you have the full model, and then you have the code generation, and then at the end you basically end everything. So far we have looked at electrical motor modeling. So the same equations that we used for the fixed wing aircraft, they are used for the motor modeling. And then whenever you use a motor, what you need to do is you need to do the parameter estimation. So you can do that. And then you can provide certain control input to the motor, see the response of the motor, and then come up with the inertia properties, the damping properties of the motor. I would encourage you to read through this. If you have taken, or if you are taking EGR 550 mechatronics systems, Professor Sugar teaches the exact same thing. So, and the next part is I will talk about the linearization and control. You are welcome to look at trimming, linearize, and the control design, but we haven't looked at it. That is the topic that we are currently discussing. So basically you combine thrust and gravity, feed it to the forces, and finally you integrate that into your vehicle model and then do trimming and linearization. So basically you do linearize. So one thing I want to tell you is, if you really want, you can take the exact same simulink file and kind of change or tweak it so that instead of quadcopter, it can do the fixed wing. Or you can do maybe some other exotic flight vehicle. And last but not least is finally you have this full model. And this specifically pertains to the quadcopter, but you have this complete full model. And then you can actually use that model and generate the code. So that is next part. So you'll see that, as you can see, there will be roll and saturation limits because the actuators saturate, and then you can do the code generation. So when I'm going to teach quadcopter modeling, I'm going to follow the exact same process, but there is something else that I want to tell you, and that is actually more interesting, is if you were to go to this, and we did this, we solved this problem. Basically, there is an issue, something called as a sling load. What does the sling loading means? That you have a helicopter or a quadcopter, but what you have is you have a rope and then you have a weight. So this sling load problem is a very common problem because, for example, rescue function. So if you want to rescue someone, you will drop a rope and that person will grab onto the rope and then the helicopter needs to take off. So that is a sling load problem. Or if large weight needs to be carried. So this problem is on the sling load. So basically, so if you have a different flight vehicle or if you have something else, you can also do the same, you can follow the same process. So basically what you have is so you will see that you have the quadcopter and then you have basically the sling load that is actually being carried by the quadcopter. So I would encourage you to play with this. So this is nothing but, and then there is this quad with a pendulum. So if you want to play this movie, this actually takes the quadcopter, and then you will notice that quadcopter has, yeah. So basically the pendulum is on the quadcopter and it goes back and forth. So I would encourage you to play with this. So there's one just for quadcopter. There is one with quadcopter and pendulum, and there are multiple utilities over here that actually would be very helpful. So with that, I'm going to stop here. I hope you will play with this. And if you have any questions, I would be happy to answer. Any questions?